So for question one, we have shown that ln of x is a linear transformation. Now we want to prove that it's isomorphism. Now, if we look at these two vector spaces, the dimension of R equals 1, and the dimension of R plus also equals 1. Right? So this would show that it's isomorphic, but we're asked specifically to show they're isomorphic by showing ln of x is an isomorphism. Now, for a linear transformation, there are two nice ways we can show it's an isomorphism. We can either show that ln of x is surjective, or injective. I'm going to show it's injective, and I'm going to solve for the kernel of the set containing the zero vector. So I'm going to solve for the kernel of ln of x. So I'm looking for ln of x equals the zero vector. And now here, the zero vector is going to be 0. So ln of x equals 0. Well, this implies that e to the ln of x equals e to the 0, which implies that x equals 1. Now, as 1 is the zero vector for set x in R where x is greater than 0, we have shown that ln of x is, or we should say that we have shown that the kernel of ln x equals the set containing the zero vector in R positive. Thus, ln of x is injective as dimension of R equals the dimension R plus. This implies that ln of x is isomorphic. Therefore, the set R plus and R are isomorphic. Here, R plus is defined as the set of x in R such that x is greater than 0. Or your real positive numbers. For B2, we're asked to show that the trace equals lambda 1 plus lambda 2. So for this one, we just need to compute the eigenvalues. So let's take the determinant of A minus lambda, B, C, D minus lambda. And this equals A minus lambda, D minus lambda, minus B, C. And what a lot of people are afraid to do here is actually compute these eigenvalues. They want to do a whole bunch of clever things without just computing what the eigenvalues are. So here, if we expand it, we get lambda squared minus A plus D lambda plus AD minus BC. Now, we set this equaling to 0 to solve for our roots. And to solve for the roots, we just apply the characteristic polynomial. Lambda equals A plus D plus or minus the square root of A plus D squared minus 4 AB minus BC all over 2. Well, we'll let lambda be the positive one. And lambda 2 be the negative one. Now lambda 1 plus lambda 2 equals, well, this is going to be 2a plus d over 2 plus square root a plus d squared minus 4ad minus bc over 2 minus square root a plus d squared minus 4b ad minus bc all over 2, which equals a plus d, which equals the trace of a. And we get that the sum of the eigenvalues equals the trace. Now, this is actually something we can generalize, but it's cool to do it explicitly here. Now, suppose that A is a non-zero, a trace zero non-diagonal matrix. Prove that A is nilpotent. Now, here we've got two things. We've got trace zero and non-diagonal. Now, in order to be non-diagonal, the algebraic multiplicity of lambda cannot equal the geometric multiplicity of lambda for at least one lambda. Now, as A is a 2 by 2 matrix, the algebraic multiplicity of lambda equals 2. Thus, we have one repeated eigenvalue. As the trace equals 0, lambda plus lambda equals 0, implies that 2 lambda equals 0, which implies that lambda equals 0. So we have that our lambda equals 0. Now, because our lambda equals 0, as lambda equals 0 and the algebraic multiplicity is 2, and A is a 2 by 2 matrix, the characteristic polynomial of A is equal to x squared. Thus, A squared equals 0. Therefore, A is nilpotent. Now, as A is non-diagonalizable, it cannot equal 0, 0, 0, 0, as this is, by definition, diagonalizable. Therefore, A is a nilpotent matrix, but is not equal to the 0 matrix. Now, this question pulls a whole bunch of theory together. To get this really clever result. We're pulling algebraic multiplicities. You have to know what nilpotency is, all that kind of things. And in this question, where we had a 5-mark question, this was 4 marks, 1 mark. The 4 marks were, could you do the calculation? The 1 mark was, there's a really clever thing you can say if you know a bunch of details. Can you figure it out? And this is hard. Putting this together is a hard question. But it's not worth much. So for these harder questions where you look at it and go, oh, there's a lot of detail there. I don't know if I can quite get the exact thing that's going on. Come back to it. Go through the rest of the exam, see if other things pop up, and then come back to this question. So now here we want to prove for B3, we want to prove three things. We want to prove that it is a linear transformation. We want to determine whether or not it's diagonalizable over the real numbers, if it's defined over the reals, and we want to determine whether or not it's diagonalizable if it's defined over the complex. So to prove it is a linear transformation given a general field, what we're going to do is we're going to let x and y be in F2, show that and C is in F, show that CT x plus ty equals T cx plus y. Okay, and this we're going to leave as an exercise. This is definitely something you should know how to do. Now, we're going to focus in on the diagonalizability and not diagonalizability. So if we look at this matrix representation, we can use the matrix representation to determine the eigenvalues. So here we get 1, 2, -3, 4. And this is T represented using the standard basis, E1, E2. Now the determinant of 1 minus lambda minus 3, 2, 4 minus lambda is equal to 1 minus lambda, 4 minus lambda, plus 6, which equals lambda squared minus 5 lambda plus 10. Now, lambda equals 5 plus or minus the square root of 25 minus 40 over 2, which equals 5 plus or minus the square root of minus 15 over 2. Thus, the eigenvalues, or the roots of the characteristic polynomial, are complex. Therefore, there are no eigenvalues. Thus, we have no eigenvectors. Therefore, no basis composed of eigenvectors exists. Thus, T is not diagonalizable. So over the reals, we're not diagonalizable, but for complex, we are diagonalizable, as there are two distinct roots. There are two distinct eigenvalues. Thus, T is diagonalizable. You should probably add some comment about the roots being complex. Well, that's in my field, but that's the idea of part C. This is the end of the part B questions. Tomorrow, I will be uploading the part C questions for this exam.